All right, we're going to look at some exponential models. This is the kind of basic layout of the exponential model. Y equals CE to the KT. C is your initial amount. It also corresponds to the y-intercept. When we say initial amount, what we mean is at whatever we're calling the time equal to 0. So, that might be, like let's say 2000, might be 2020, whatever we call time 0, this is the amount at that moment. And then K is our rate. And if K is positive, then we have a growth model. And if K is negative, we have a decay model. Now, we've already seen in a previous section this formula, and that was for compounded interest continuously. So this is a perfectly fine formula to use for this model. I mean, the letters don't really matter. P is your principal investment, how much you start with. R is your rate. So we can see those two things are matching up exactly. And then usually we're talking about time and an amount. How does that change? How does the time change? How does the amount change? Same thing here, time and amount. Those are the two variables that are going to be changing. So we're not going to use X here. We're going to use time for most of these problems. So let's see a kind of a typical type of situation you would see with these exponential models. So let's say you had a town, had a population of 50,000 in 1980. In the following decades, the population underwent an exponential growth. In the year 1995, the population of the town was 80,000. Find an exponential model for the population and use it to predict what the population should have been in 2010, round of the nearest things. I probably should have said in here, let t equals 0 be 1980s. Kind of indicated that way it was said, but I should have been explicit and put that in there. All right, so I'm looking at the model, and I'm just going to use the PERT formula here, just kind of stick with that. And so I know my initial population. My initial population, the one I'm saying is time 0, that's 1980, was 50,000. All right, so to figure out this model, what I need is my rate. And so that's why typically they'll give you this other point in time. They'll say, okay, at this other point in time, you had a certain amount. So I'm going to say, okay, I have an amount of 80,000 here. I'm looking for my rate. And my time is going to be how many years after 1980 this is. So that's going to be 15 years. So that's going to be my time, 15 years. Since I'm letting 0 be 1980, this would be 15. And then to solve for these in here, again, from the video about how solving exponentials, you got to get this part by itself, and then usually we'll take the logs both sides. So there's a little pattern here. For most of these problems, you're going to divide, then you'll do ln, then you'll divide. So I'm going to divide by 50,000. That's going to cross off that. That's going to give me 8/5, which will come out nice if I want to put that in a calculator, but typically this is going to come out to be a nasty thing, so I don't want to usually do that. Then I'm going to take the natural log of both sides. Natural log of 8/5 equals, and natural log of e, you're going to cancel each other out, and you're going to get 15r. And then to get r by itself, I'm going to divide both sides by 15. And my r is approximately, I'll throw that in the calculator, natural log of 8/5, close that up, divide by 15. And so the growth rate here is going to be 0.03, we'll just say 0.03. And so my model is going to be, oops, I already know my P. My P was 50,000. So how much did I start with? Again, now I know my rate and time. So there's my model. Then it says, use this to predict what the population should have been in 2010. So again, I'm going to ask myself, how many years later is that from 1980? In this case, that's going to be 30. And I'm just going to plug that in for my time, times 30, and round to the nearest 1,000 people. So 50,000. Remember to get to E, second ln, and then 0.03 times 30. Close that up. So it looks like the population should have been 123,000 people in this town. So if they had continued on that growth rate up to 2010. Now, probably not, because a lot of times you'll see a population kind of grow and then it'll kind of flatten out after a while. But, you know, just looking at this model, this is what it looks like. All right. Another type of exponential model, or another thing related to exponential models you might see, is half-life. And usually we're going to talk about it with radioactive decay, but half-life can refer to other things, anything that is kind of going through an exponential decay situation. You can talk about how long it takes for half of whatever you're looking at to decay, to get rid of, to break down. You know, if you have like a drug in the blood, and how long would it take that half of that drug to break down? It might go through an exponential decay model through that. Okay, so let's say we were looking at this. We were told nickel-63 has a half-life of 100 years. Find the annual rate of decay of nickel-63. Now, the problem there is, whoa, what's going on here? The problem there is it doesn't seem like I have a lot of information. And what I'm going to do is I'm going to pick an amount to start with. So I'm going to pick, I don't know, 10 whatever, grams, kilograms, tons. It doesn't really matter to start with. Okay? Because what happens is, however much you have, you know, if I have 100, after, or sorry, if I have 10, let's do 10. I have 10, and 100 years go by, I'm going to be at 5. And then after another 100 years, I'm going to be at 2.5. And after another 100 years, I'm going to be at 1.25. What's happening is every 100 years it gets cut in half again. So it really doesn't really matter how much I start with. You know, you could say, well, maybe I started with 20, and you know, 100 years went by, and now I'm at 10. So just pick a number to start with. I'm going to go. Starting with that, I'm looking for the rate. So I need a time and an amount, and I'm just going to, you know, say, okay, well, let's let 100 years go by, and because that's the half-life of my nickel-63, I'll let 100 years go by, and that's going to take me to half of what I started with, so in this case, 5. And so if I'm looking for one of these things in here, again, the pattern was you divide, you do ln, and then you divide. That's this little shortcut pattern here. I'm going to divide by 10, get a half, e to the 100r. I'm going to do the natural log of both sides. Natural log of 0.5 equals 10r. Again, ln and e cancel, sorry, equals 100r. ln and e cancel each other out. And I'm going to divide by 100. And I'm going to get my rate, my annual rate of decay for this. Natural log of 0.5 divide by 100. And there's my annual rate of decay. So negative 0.0069, we'll say. You'd say 7. I'm always worrying about just giving it a little bit more information. Now, real quick, let me kind of show this notation. Let's say I divided by something a little bit bigger here. I just want to be clear what this notation is saying. So I'm done with this problem, but just kind of what does that notation mean on this calculator? This would mean negative 6.93 times 10 to the negative 7th. That's what this e negative 7 is saying. This is how this calculator shows this scientific notation. So if you see something like that, that's what it's saying. Make sure you, when you write the rate, you write that part, times 10 to whatever that power is. But I didn't have that on this problem. So our rate was negative 0.0069. Let me, real quick, I'm just going to pull that back up so I can see it. So on this next problem, now that I know what the annual rate of nickel 63, I can do other problems with nickel 63. So let's say I had some sample and there's only 20% of my sample, the nickel 63 remaining in the sample. How many years must have gone by? So again, they're not telling me how much I start with, but if I think about it, this is about percents. So what percent of the starting amount is the starting amount? And that would be 100%. So if I start with 100, I'm down to 20%, or 20 out of 100, then I can find the time. I know the rate, we just calculated it, negative 0.0069 t. And so again, anytime you're looking for R or T, you're going to do the divide, ln, divide. So I'm going to divide by 100. So 0.2 equals e to the negative 0.0069 t. Do the natural log of both sides. Again, natural log and e will cancel each other out, giving you negative 0.0069 t, and then divide both sides by that. Okay, and t is approximately, now let's see, natural log of 0.2, close that up, divide by negative 0.0069, and it looks like it's about 23 years. 23 years. Which, if you look at my little model here, or sorry, what did I say, 23? 233 years, sorry. 233 years. If you look at what I said here, after 100 years, you'd be at 5. After another 100 years, so 200 years, you'd be at 2.5. So somewhere between 200 and 300 years, we're going to hit 2. That makes sense. We got that 233. So that did work out. And then another problem, compounded interest. So you could do the PERT. I'm not going to do the PERT formula because basically I've been doing the PERT formula for all these others. So let's say we looked at, what if it's compounded monthly, the other formula? How long would it take to triple an investment? Compounded monthly at an annual rate of 6%. Now, again, they're not telling me how much I start with, and that's because it doesn't actually matter how much you start with. It takes just as long to triple an investment of $100 as it does to triple an investment of $1 million. So it doesn't matter how much we start with. We just pick something to start with. We do need to know that we're compounding it monthly, so 12 times a year. So I'm just going to, again, pick a value for P. So I'm just going to say 100. Okay, it doesn't really matter. I'm just going to pick that. And so I go to my formula for compounded a specific number of times a year, in this case 12 times a year. And I'm going to say, okay, if I invest $100 at a rate of 6%, and turn that to a decimal, 12 times a year, I'm looking for T, and I want to know how long it takes to triple. Well, if I triple 100, I now have 300. And so even though there isn't an E in here, I'm still going to go through that process of divide, ln, divide. I'm still going to do that here. So I'm going to divide by 100. That's going to give me 3. That's why it didn't matter what I invested. I have this formula, 12t. I'm going to take the natural log of both sides. Now, unlike E, this is not going to cancel out. But what I can do is I can now take my exponent and move it out front. That's a property of logarithm. So I'm going to say natural log of 3 equals 12t natural log of 1 plus 0.06 over 12 there. And now I want to get t by itself. So I'm going to divide both sides. I'm going to divide by the 12. I'm going to get rid of that. and the natural log of 1 plus 0.06 divided by 12. And that's going to give me p is approximately, and I'm going to put that in my calculator, natural log of 3, that's my numerator, divided by, I got multiple things on the bottom, so I'm going to have to put the whole bottom in a parenthesis, 12 natural log of 1 plus 0.06 divided by 12. Close that, close the bottom. It looks like it's going to take me about 18.4 years to triple my investment. If it's at a 6% compounded monthly. So there's some different types of exponential models. There's so many more types of exponential models. This kind of gives you an idea of the basic ones you're going to see when we're doing this course.